Part A, we are asked so what do we mean by this? You expand this. This is multiplication basically. There is an operator A and a number, an eigenvalue. You again write it like this. And so on. And we need to prove that this is ultimately a null operator. So it will not do anything. Everything will just vanish or become zero. Okay, let's try to see. Okay, so if I write an identity just right side to this, what will I have? Is a minus a prime. Let's say I'm using identity like this. We can expand this further, of course. For simplicity, I'm just taking one term right now. So when a will operate on this, what will we have? We will have a prime, a prime, a prime, minus in the same term, prime. Right, so these are same thing. This will be 0. And since all of these are in multiplication, so this will ultimately become 0 or 0 operator. Okay. Next, we are asked to check the significance of this. This is different. Okay, so let's say these are numbers, denominators are just numbers, there is only one operator, and we need to see what we can do with it. Okay, so we can check what is this part. So again, we can try to use identity here. And so this is plus a prime. This is only the first term. There will be many such terms like a triple prime is not equals to a double prime and so on. All this such that this denominator is not 0. I'm only currently talking about the first part. So, okay, yeah. And this a operates on a prime, we get a prime minus a prime. There is still left, which is nothing but the identity operator. Okay, so this is what it means. But if I want to operate this on some state alpha, so again there are lots of terms, but I'm looking at the first part only. and I'm using the identity in between. So there is A prime alpha. This is a number. Let's I name it just C alpha. This A will operate on A prime, and again I will have prime minus double prime minus double prime A prime. It is like C alpha A prime. So this is like a projection operator, because when we have a projection operator okay, like this, which operates on some state alpha, you get a number multiplied by a basis vector. So you are projecting on some basis, and this is the number. So this acts as projection operator. So next, what we are supposed to do? We should verify this by using the A as spin Z operator. Okay, so how we are going to do that? So A is SZ, and the eigenvalues corresponding to that are plus h bar by 2 is minus h bar by 2. Okay, so if we look at this, A prime, which is not equal to minus h bar by 2, of course, there is z minus h bar by 2. If I take this difference, will be h bar by 2 minus plus 2 is nothing but z minus h bar by 2 plus h bar. Okay, so when we operate this on state alpha, we know that the identity is defined as okay, so that will be basically okay, what I can write is yeah, there is plus and there is minus, and this will act alpha, because identity is A prime some basis state. In our case we have two, plus and minus, so we have this, there is C plus alpha, C minus alpha, where I have decided C plus minus is plus or minus alpha. So I made a mistake here. will not be, because it will plus, it will be minus, right? Alpha is absorbed in this coefficients. Okay, so C plus is okay. So these are eigenstates of SZ operator. So one will give me plus h bar by 2, another will give me minus h bar by 2. So we have there is C plus is h bar by 2 minus h bar by 2 h bar plus is minus h bar by 2 h bar C minus minus. So this will be 0, and we'll be left with minus C minus minus. Same thing we can do with, if we had chosen here plus h bar by 2, answer will be here C plus plus. Okay.